Hi, my name is Camilo Fosco and I will be presenting the results of a collaboration between MIT, Harvard, and Adobe. Let's start with this. An image will appear for a small amount of time. What captured your attention in it? Most of you probably saw a large humanoid statue, something metallic maybe. Others might have noticed some vague details about the surrounding scene. Let's do it again. Okay, so what about now? Where did you distribute your attention this time? Most of you probably attended to the little girl and boy close to the hand of the statue. Some of you probably explored the scene, the tents, or the other pedestrians. It seems that your attention was distributed differently this time around. With an increased viewing duration, the parts of the image that we pay attention to change. This is the key driver of our work. Attention patterns change as viewing duration increases. The image shown before was first displayed for 0.5 seconds and then for 5 seconds. You probably noticed that attention shifted from the statue to the secondary salient elements. In fact, attention might have shifted in a similar manner as the white regions showed here. These regions correspond to the areas scanned by multiple viewers at the same viewing durations, based on actual data we collected. It is clear that attention changes over time. However, current methods to collect and estimate these attention maps disregard this temporal evolution. They are usually limited to human attention data collected at a fixed viewing duration. In this work, we propose to collect and then predict different attention maps for different viewing durations. We introduce multi-duration saliency and make 3 contributions in this space. First, we present a new dataset for multi-duration saliency, collected with a UI that explicitly allows us to measure attention patterns at different viewing durations. Second, we introduce a model to predict multi-duration saliency from an image and show that we improve upon the state of the art in both traditional and multi-duration saliency estimation. Third, we exemplify how our framework can enhance existing image applications, such as automatic cropping and captioning. But first, what is multi-duration saliency? For some context, let's consider traditional visual saliency, which aims to estimate the attention patterns of humans on a natural image. There is work proposing saliency models, which take an image as an input and return a saliency map, a heat map that indicates what parts of the image are more salient and thus more likely to be attended to. As mentioned, this approach does not take into account viewing duration. The predicted heat map corresponds to attention patterns it produces at a fixed viewing duration, the viewing duration used to collect the dataset the model learns from. A multi-duration saliency model, on the other hand, produces distinct maps that highlight what is salient at different viewing durations. To understand the context around multi-duration saliency, let's analyze how it compares to similar techniques in the field. When considering attention in a static context, fixed viewing duration, a single individual contributes a set of fixations, and aggregating these fixations over many individuals generates conventional saliency maps. As we mentioned, this approach loses track of the temporal aspect of attention. Now, scan paths, another well-studied alternative for representing attention maps, correspond to an individual's exploration path over an image. Although scan paths yield temporal and ordering information, they lack consistency across observers and are thus difficult to aggregate. Our approach explores a fourth alternative, modeling population-level maps for different viewing durations, effectively providing the consistency and generality of population-level maps while simultaneously capturing the temporal evolution of attention patterns. The first challenge is collecting a large-scale dataset to allow us to model these changing patterns in attention using crowdsourcing methods. There are several existing frameworks for capturing crowdsourced attention data, such as bubble view or import templates. But none of these techniques support measuring saliency at different durations. We aim to collect data while controlling viewing duration, so we need a different approach. We opt to use the code charts UI, which is an interface that allows for crowdsourced collection of fixations at specific viewing durations. The code charts UI works the following way. An image is shown for a fixed viewing duration before disappearing. A grid of 3-character codes is then rapidly shown for 400 milliseconds, allowing users to remember the code located at the current gaze position without having enough time to explore the rest of the grid. Finally, users input their 3-code character, saving their fixation location for the given viewing duration. Fixation crosses between images and validation trials spaced throughout the experiment are used to recenter the gaze and ensure data quality. By aggregating responses from 50 participants per image and viewing duration, we obtain code charts 1K, a dataset of multi-duration saliency. The dataset contains 1,000 images with attention data at 0.5, 3, and 5 seconds, which were determined in a pilot experiments to be the most different from each other. Here are some examples of the collected data. The dataset is composed of varied subsets of images from different computer vision datasets, ensuring that a large range of image types, scenes, and actions are represented. We include images from classical saliency datasets such as Salicon, as well as unconventional images from datasets like abnormal objects, out-of-context images, or LEMM, an image memorability dataset. Now, analyzing the collected data yields interesting insights. Viewers focus on faces at small exposure times, and manipulated objects or action targets are attended at longer viewing durations. We observe several interesting patterns when we focus on face saliency. We see first the boomerang pattern, where viewers shift their attention from faces to then actions or the attended object, decreasing the overall face saliency, and then back to faces. This is related to a phenomena commonly referred to as inhibition of return. We show a few examples here. The decreasing pattern is also interesting, where it simply consists of a shift of attention from faces to other image elements, and that pattern occurs in 24% of our images. We show some examples here. Armed with this data set, we build a convolutional neural network to predict saliency at different viewing durations. Our model is built with lightweight modules and can be trained with both traditional saliency data as well as CodeCharts 1K. There are three main components. First, a strong encoder based on state-of-the-art convolutional neural networks, then a custom temporal excitation module that deals with the temporal aspect of our modeling, and finally, a simple regularized decoder used to obtain our final time-specific saliency maps. The key to generating accurate multi-duration saliency maps without overfitting is our lightweight temporal excitation module, or TEM. This module outputs features for different viewing durations by iteratively transforming a compressed representation of the image. First, the feature maps generated by the encoder are averaged across width and height, and pass through a fully connected layer, which reduces the dimensionality of the feature vector to 512 dimensions. Then those vectors are replicated 3 times and fed to a recurrent network, an LSTM in our case, and the output of the LSTM is essentially 3 vectors that contain information specific to each time step that we want to reproduce. And those will essentially be used to rescale the feature maps inputted to this module after passing the vectors through a fully connected layer. The model is first trained on a large traditional saliency dataset, Salicon, before being fine-tuned on CodeCharts 1K. During Salicon training, 3 losses for comparing saliency heat maps are used. Normalized scan-path saliency, which aims to maximize the values of the predictions at each ground truth fixation point. Correlation coefficient, which encourages high correlation between the ground truth and predicted maps. And finally, the callback lively divergence, which aims to minimize the distance between the distributions derived from the ground truth and predicted maps. When training on CodeCharts, we include 1 more loss of our design specific to multi-duration saliency, the correlation coefficient map. This encourages our model to produce similar maps at adjacent durations when the ground truth is similar, and distinct maps when the ground truth is different. Let's talk about multi-duration saliency evaluation now. To evaluate our model, we first require baselines with the same ability to output different feature maps for different durations. For that, we adapt existing well-performing saliency models to our framework. We train 3 separate SAM networks from Cornet et al. On the subset of data corresponding to 0.5, 3, and 5 seconds. And we also adapt the internal functioning of this well-known module to output saliency maps at each time step. Our results show a clear advantage over existing alternatives with a 57% reduction in parameters over the runner-up. Qualitatively, we observe that our model generates distinctive maps for different durations. The shifts of attention we observe in the human data are well approximated. We also compare our model to several existing alternatives in traditional saliency, such as EMLNet, SALNet, and SANResNet. And in traditional saliency, our model also performs well, particularly under the NSS metric. We achieved the highest NSS score, and at the time of submission, this result scored 2nd on the LSAN 2017 saliency benchmark. Our model can be used for multiple applications. Here we show how our saliency predictions can be used to focus on image captioning module on regions that should stand out at different viewing durations, producing diverse captions. Removing the non-salient visual clutter can benefit caption quality. By cropping around zones of high saliency, we can generate thumbnails conserving salient content. Our model allows for different thumbnails adapted to what is intended at different viewing durations. These automatically generated image thumbnails, shown here, often contain close-ups of the most important objects at shorter viewing durations. Finally, we show that multi-duration saliency heat maps can indicate the order in which regions in an image should be prioritized to provide a seamless viewing experience in image loading or compression scenarios. For instance, for displaying search results or rendering image content for simulations or VR. So in conclusion, we propose a scalable, crowdsourceable technique for gathering ground truth multi-duration saliency data. We use this to collect the CoreCharts 1K datasets that we've shown here, which is the first dataset of multi-duration saliency. Our recurrent-based model is a top performant at predicting conventional saliency while also providing predictions on multiple durations. And we show first approximations of how our model can be used in different applications and enhance the models existing today. Thank you so much. Thank you for your time. And to facilitate further research in this area, we make our multi-duration saliency dataset model and code available at this link. Thank you for your attention.